Good afternoon to all of you. Let's start the work today. I hope you all can hear me clearly and see the screen too. Now, remember, we have already finished with the 8th chapter in the last lecture. Today, now with the 8th chapter, we have finished first unit. The first unit was the longest unit and it was dealing with the concept, a complex concept like psychoacoustics, where there are many aspects of the subjects. Subsequently, as we get into further units, the number of chapters per unit would be little less. Also, the chapters are little smaller. Also, the conceptual complexity decreases, and many things that we have already done is now will be repeated in other aspects. So, life is going to get easier from now on. Now, in the first four chapters that we did, we spoke of perception of sound. How do we perceive the sound? Now, in this section that we are taking up right now, we are going to talk about the generation of sound. That is the important idea that we will explore. So, there are three components to the discussion. We are going to take one set of musical instrument in the first part, in the first section. In the second section, we are going to look at human vocal cord and its abilities. And in the third section, we are going to look at loudspeaker, construction, making, working, etc., of a loudspeaker. So these are the three things we are going to explore. Remember, there are number of sound generating devices. In fact, musical instruments has large numbers. You have string based instruments, you have percussion based instruments and others. We are selecting just a woodwind instrument. We are not selecting the the what you call string based, because many of you have done sonometers in detail and you know that most of the string based instrument they use the principle of sonometer. So we are not repeating it, we are looking into woodwind instrument. Of course, percussion based instruments are also there, which ideally we could have covered, but as I said, there are so many aspects of sound that we cannot cover in one single course. So this chapter right now that we are going to start with is about woodwind instrument. Then what is a woodwind instrument? You're all familiar. The instrument where you need to blow the wind inside and some sound is generated. There are a variety of such instruments, from a normal toy CT to a flute to an expensive clarinet. Anything can fall in this category. Traditionally, these instruments were generated using wood, bamboo, or something similar. Therefore, they were generally called as woodwind instruments. But present day, there are many other materials used like plastic, steel, etc. Purists still stick with wood. We put all such instruments under the category of woodwind instruments. So that is what we are going to talk about now onward for few lectures. The one reference device that we will use is a clarinet, and in that context, keeping that device at least in the first part of this chapter and center, we are going to talk about how does it work, how does it vibrate, how does it produce the sound, what are the impact of holes, etc., etc. So today is kind of an introductory lecture. So let's go ahead. So whenever an air column is suitably excited, it gives a sound. You can do it, test it anytime. I have my pen cap in my hand, and if I try to blow tangentially, it will produce some sound. So as you can all hear this sound is presented to you just by blowing the cap of the pen tangentially. You can try this, it gives sound. Now what happens in this process, that the air column inside the cap gets excited, starts vibrating, and it produces sound. The vibrations which are produced are generally of two types. There is one type in which a reed is placed. I'll show you what is a reed. A reed is placed. It's a thin vibrating device or vibrating sheet. Uh, if you have tried in if you have ever tried an eclairs chocolate wrapper, you stretch it, keep it between your lips and blow across it, you will hear a musical sound. If you take a banana leaf and do the same, you will hear a musical sound. So if you stretch a chocolate wrapper, keep it across your lips, make a small gap and blow over it, then it acts like a vibrating sheet, which is like a reed here. So these are makeshift reeds. There are permanent reeds also available. So all these are used to generate the sound. And there is another example is a vibrating air stream type. One example which I showed you was just now the cap sound, pen cap sound. It's a vibrating air stream, also sometimes referred as air reed. Here you don't have a physical reed there. Another way to make a reed is you take a straw, plastic straw. Of course, these days they are not available. Paper straw maybe. You press on one edge and try to blow across it, and you will get a sound. The professional reeds used in professional instruments are made using wood. Most of the instruments also these kind are made up of wood. That's why the name Woodwind Instruments. There's a number of examples of woodwind instruments. You have a normal flute, which are used in Western music particularly. Normal flute, clarinet, saxophone, oboe, or oboe, whichever way you pronounce, bassoon, clarinet, etc. So, no, this is clarinet. This is not a clarinet. This is something else. I think it is um, called. I'm forgetting something else you call it. It's called a register, I guess. Last one is register. So these are all the instruments mostly used in Western theaters. Indian woodwind instrument. There are a couple of them. Uh, you all know Shehnai is one. Indian flute is another, which is very popular. In fact, the transverse flute or side blown flute is the only flute which is played in India. I mean, all over the world, it's of its kind which is played in India. While the normal fipple flute, where you blow into it longitudinally, it is practiced all over the world. A typical example of a transverse blown flute is over here. You will find that this is the embouchure or the hole through which you blow, and this is the air column inside that vibrates. We will discuss this towards the later part of our chapter. Here is a small flute recording. It has a wonderful sound, soothing and mesmerizing. So that's a small flute recording for us. Going ahead, we'll focus on clarinet. That is the first focus in our chapter. Second focus is of course the flute. We'll come to it a little later. In the meantime, if you have a, okay, I'll tell you after the, for practicals and others, we will talk about it. A clarinet has a cross section of this type. Typically, it has a long tube here, and it has a front portion which has a vibrating reed here. You can see a very thin sheet, and it has a bell over here towards the end. These can be removed. You can remove this part, you can remove this part. So that's how the clarinet look like. Bore diameter is around 15 millimeter. So this diameter is around 15 millimeter. It uses a single reed, 0.1 millimeter thickness at this end, and opening is 1 millimeter. This opening, small opening, is 1 millimeter. Natural frequencies vary between 2000 Hz to 3000 Hz depending upon what is the length of the tube. And for softer tones, if you blow very softly, then reed will not go and touch up. While if you apply a larger pressure, then this will touch touch the upper end, and then it becomes a closed end. So if it is open, then if you are blowing into it softly, then it acts like an open tube. But if you blow it into hard with high pressure, then it acts like a closed tube. Bernoulli's principle can explain the functioning. Let us this is the example of the reed part. This lower part is the reed, which is a replaceable reed. Say if they get broken or dis distorted, you can put a new reed there. So this diagram actually explains how the working of a reed system happen. So as you blow into it, the blowing pressure will compress the air in front, and the compression will travel in the medium. But as you blow this inside, then the velocity increases and the pressure drops. As the pressure drops, outside pressure is still high, so the reed tends to move towards inside. So that is the first thing happens. The high compression travels to the lag end, and it's a high pressure zone created here. Outside is a low pressure, so basically the wave hits a rarer medium. Now from the basic science we know that if a longitudinal wave hits a rarer medium, then it loses its energy. I mean, a compression is reflected as a rarefaction. So a rarefaction, which is shown by a trough here, just for the representation purpose, there's a phase inversion happening. A rarefaction travels back onto this side. So get reflected as rarefaction, while reed vibrates back. So reed goes up and reed blocks the mouthpiece. So as the reed goes up and reed blocks the mouthpiece, the rarefaction is reflected by a closed end, which is a hard surface. So you all know again the theory that if a longitudinal wave is reflected from a hard surface, then rarefaction is reflected as rarefaction. Means there will not be any phase change. So no phase change occurs. The rarefaction is reflected as a rarefaction, and it goes on to this side. But the reed's elasticity will force it to open now. So it starts opening. While this rarefaction travels at the other end. Remember, at the other end again is a medium which is rarer. So after reflection, it will get converted into compression, and the compression is now traveling back. So as the compression travels back, you will get onto this side. In the meantime, if you are blowing continuously, you can introduce the next compression and even that will travel. So this way the cycle repeats. Remember, in multiple reflection, as it goes ahead, the intensity also drops. So once it is reflected from this side, it will not be that strong. But in the meantime, next compression will be introduced, reinforcing the previous one, and the vibrations will go ahead. That is how the reed pipe system vibrate and produces sound. Now, air column vibrates with its natural frequency while the reed undergoes forced vibration by the air column. So remember this. This is an important fact about clarinet. The air column will vibrate its natural frequency. You know the air column vibration formulae that will work. Reed undergoes forced vibration by the air column. Reed can close open two times again during the one round trip of the pressure pulse, and it happens at high embouchure pressure. Embouchure is the mouthpiece at which you blow into it. So at high pressure, as we have said, the reed will open and close completely, and you have seen that the wave travels two times in one opening and closing of the reed. So in this one, the frequency is three times the fundamental frequency. The frequency that is being produced is three times the fundamental frequency. Now, the frequency is V by 4L. This is the fundamental. And these are the higher harmonics which are present. So three times, five times, etc. So that formula will apply. How would it affect, how would the bore type or type of the bore that will affect the clarinet? So or in general, as I said, we are keeping clarinet in the center and talking about, but we can extend this discussion to some other devices too. So the bore can be of two types mainly. One is the cylindrical bore, while the other one is a conical bore. Now in conical bore, as you can see, in cylindrical bore, different harmonics are generated with the same strength. But in conical bore, the different harmonics are not generated using the same strength. You can see that this wavelength is different, this wavelength is different, this amplitude is different, and this amplitude is again different. Here, this is large, small, and small. So bore type affects the harmonic relationship. Normally cylindrical bores are used for flute and clarinet. Conical bores are used for oboe, English horn, bassoon and saxophone. If it's a conical, then you can apply the length formula here. But remember, the amplitude ratios are not same as that case of cylindrical. Here is the cylindrical, conical and flared tubes of the same length but different modes of vibrations and the frequency that they will produce. So this table gives you some data to compare. Now, another interesting part is the tone hole, impact of the tone hole. In fact, study of this is a very good project work. How does it happen? So if your tone holes are the holes that you had seen on flute, the image that I had shown. Even on the clarinet there are tone holes. So you press or open the tone holes. The moment you press or open the tone holes, you will actually effectively changing the length of the tube. As you change the length of the tube, your resonant frequency changes and you can create different tones. That is why they are called tone holes. Now, first study that has been done is the size of the tone hole. So, larger the hole, more effective length is shortened. So, for example, here it's very small. Remember, if you if you have a large hole over here, then this part of the tube get in connect with the surrounding pressure, and the pressure drops, and in fact that is equivalent to shortening the tube. But the size of the tone hole is very important. If it's very small, then it is not very effective. You may feel that length is here, but if you make it little larger, then the length of the tube, it reduces effectively. The frequency will increase if you make it larger and larger. Now, if you find, or if you compare the tone hole with the bore diameter, so that is the comparison factor. If the tone hole diameter is equal to the bore diameter, then the pipe is effectively shortened here. So if you have a large tone hole, then this, if it is open, then it is as good as length of this much. This much is extra or redundant. So be careful. Look at the size of the tone hole if you are buying any flute or clarinet anytime. So this becomes a very important and interesting project to work. Some people have worked on it earlier. Suppose if you have a tube or a flute or something like that, you can take a flute, close all the holes first with a tape, then you can take one hole, and in that you can punch the holes of different diameters, starting by 1 millimeter, 2 millimeter, 3 millimeter, 4 millimeter, 5 millimeter, 6 millimeter. Or you can go into 2, 4, 6, 8, 10, 12. Measure the bore diameter first. Remember, you have to go up till the bore diameter. So if you can make those holes accurately, then this becomes an excellent project work. Take any flute, you can buy it from the market. Normal flutes are available 50 rupees, 100 rupees, whatever size, whatever price you and size you look for, you can get. Practice some uh, blowing into it, and then you can do this simple experiment which can give you the relation between the effective length. You record the sound. How do you get the effective length? Simple. You record the sound, play the sound in the Audacity app, use the plot spectrum feature to find out the fundamentals frequency, then take the fundamental frequency, use the formula which is given over here to calculate the length. That will give you the effective length. You will find that as you increase the diameter of the hole, the length will go on, sorry, the frequency will go on increasing, and therefore length will go on decreasing. And hence you can plot a graph as well. So you can try doing this. An excellent project work. Going ahead from this point, what happens when more than one hole is open? So if more than one hole is open, or two holes, three holes, then they act like a tone hole lattice. And in that case, it not all the frequencies will pass through. It only transmits higher frequencies, and the lower frequencies don't pass through. So it acts like a filter. It has a cutoff frequency, and cutoff frequency has a formula like this, where different A, S, B, C, I have not written, you'll have to check the book. A, B, T are the parameters over here. And this cutoff frequency actually will determine how the timbre or the harmonic spectra of the instrument would look like. So when more than one hole is open, it becomes a little complicated. But the important thing that we have to remember, that lower frequencies are still played, higher frequencies are, they pass through it. Now Next class I'm going to talk about impedance and some more parameters of clarinet, and then some other woodwind instruments like flute, register, etc. This class I would like to end with two short videos. So please have a look into it. One is from a famous clarinet player who gives us some brief idea about the clarinet, and second one is one of from my favorite movie where the clarinet is used for very interesting purpose.
The clarinet is basically just a cylindrical wooden tube with finger holes, so that as I take more fingers off the instrument, the pitch will rise. Like that, and a lot of metal keys in order to enable me to play all the notes in between those notes, the chromatic notes. And some of that metal work is to enable us to play trills, for example, quite rapidly and efficiently. Now, if I didn't have the key on the side of the instrument, that trill would come out like this, which might not particularly please either the conductor or the composer. So a lot of this metal stuff, although it looks complicated, is actually there to simplify matters for us. In order that we don't have to carry a case around which is as long as this instrument, particularly as we usually have to carry two, the instrument takes apart. And you can see there is the bell, which is the end of the clarinet, called a bell because it's bell-shaped, obviously. You then have the main part of the clarinet in a lower joint and an upper joint. And then at the very top, we have a barrel and the mouthpiece and reed on the mouthpiece, which go on the top of the barrel. Well, if you go to an orchestral concert, you may have sometimes wondered why you see the clarinetists with two clarinets, whereas all the other members of the woodwind section have just the one. And you'll sometimes see us change quite rapidly from one to the other. Now, this isn't because one of the instruments has suddenly become worn out, or indeed that we're trying out different instruments in the concert. It's just that because of the nature of the fingering system on the clarinet, most composers write for two different clarinets in order to avoid us playing in complicated keys. So we have a B-flat clarinet, which is the shorter one, and an A clarinet, which is the longer one. I'll just put a mouthpiece on so that you can hear the difference in pitch. So if I finger the note C on my B-flat clarinet, it comes out as a B-flat. And if I finger the same note C on my A clarinet, it comes out as an A. So we have to be careful to get the right instrument to do that. Sometimes composers ask for a very, very rapid change from one to the other. For example, Bartók in his trio Contrasts, which we've recently recorded as part of the Philharmonia's Bartók series, Bartók asks for a change that's this fast. As you can see, I slightly fumbled that change, and if that was a concert, I would definitely have missed it. So you have to be pretty nifty with some of these changes. That also brings up issues with the conductor, because obviously if we're concentrated on a complicated change of clarinets, we can't.
So that's a long video. I will leave the link in the description. You people can go through it. Let's watch the second video. Could clarinet fire here or not? I leave you people to figure it out. It's a 10-minute clip, so do watch it. It's interesting. With this, we can end this lecture over here. Next class, we will take it forward, and I will be available right now in the Google Meet. So anyone has to discuss anything can come. Thank you.